A2 Further Maths, Type 1 and Type 2 errors. So last year we started looking at what we call Type 1 errors. So what I'd like you to do, please, is just have a go at these two questions in front of you from last year and see if you can work out the answers to both of them and find the probability of making a Type 1 error. So if you want to pause it now, have a go at both of those, and then once you've had a go at both of them, you can start playing the presentation again. Okay, so let's have a look at question 1 then. So question 1 says you want you to carry out a binomial hypothesis test using a 10% level of significance. The sample size is 18 and the hypothesis is that your null hypothesis is the probability of 0.4. So the chance of you being successful out of this 18 is about 0.4, and we believe that there's an alternative hypothesis that the probability is actually less than 0.4. We don't believe that the probability is 0.4, we think it's less. And we're going to check that using this set of data. What we need to do is find the probability of making a type 1 error. So the first thing I need to do is just set up my table. Once I've got a random variable, I know it's binomial, it's 18, probability of success 0.4. So I can set up my table of results. I can put my x values, my successes along the top out of the possible 18 tests, and the probability that x is below a certain amount. So if I get below one of these numbers, then this is the probability of that happening. So for example, if I ran 18 tests, I got no successes at all, the chance of that happening is very, very small, 0.0001% chance. If I ran 18 tests, what's the probability I have no successes or just one success? It's gone up a little bit, it's 0.0052, it's about 0.5% chance. What's the probability if I ran 18 tests, chance of success is 0.4, and I got either no successes, one success, or 2 out of the 18 successful? That's a bit stronger now. It's a probability of 0.027, so just under 3% chance of that happening. What about if I ran 18 tests, 0.4% success, and I got 3 or less? So no successes, 1 success, 2 success, or 3 out of the 18 successful, I would get 0.091. So that's about 9% chance. Now I'm looking for a 10% level. So that's pretty close. If I got 3 or below, I would doubt this claim. Okay, I would doubt that it's 0.4 because that's very unlikely to happen. If I got greater than 3 though, if I got 4 for example, the chance of, if I had run 18 tests at 0.4, of either getting no successes, 1 success, 2 successes, 3 successes, or 4 successes is a lot higher. The chance of that happening is about 0.217. About 22% of the time, you would expect, if I had 18 tests, 0.4% success, about 4 or less is about 22% of the time. So the probability of getting 3 or less is below the 10% level. 4 or less is no good, it's above. So these are the values you would reject the null hypothesis. So if I ran this test of 18 for whatever it was, if I had 3 successes, I would doubt this claim. If I had 4 successes, that's fine, that's above that critical level of 10%. So the probability I made a type 1 error there is not 10%, it's going to be 0.091, about 9.1% chance that I've made a type 1 error. And a type 1 error, as it says there, and I'm sure you've checked it in your notes already, by rejecting the hypothesis when it's actually correct. So in that case, I would have sat there and I would have said, oh, I've got 3 successes, I doubt this claim, therefore I've got significant evidence to reject this 0.4, but in fact it was actually true. Now if that is the case, I've made a type 1 error. I've rejected the null hypothesis when in fact that null hypothesis was correct. Okay, now the difference between these two is because it's a discrete random variable, so you don't ever get the exact value of what it's saying in there. Okay, right. Want to have a go at number 2 yourself. Now I've just gone through the previous one again, you can pause it and have a go yourself. Okay, so let's have a quick look at this one then. So this one's different because it's a Poisson distribution. The hypothesis test is about the number of birds per hour flying overhead. Okay, is modelled by a Poisson distribution. So the rate that those birds fly over, they're suggesting is about 12 birds per hour. But if you're looking up in the air and you're thinking actually it looks like a lot more than 12 in that hour, then you're doubting that claim. So the number of birds that need to be observed to reject the null hypothesis using a 5% level. So exactly the same as before. First thing I'm going to do is just write out the probability distribution. So X is distributed using a Poisson distribution and the rate is 12 per hour. Okay, so I've written it out like that. I'm going to fill out my table, the same as before. Noticing this time it goes above. So I'm looking at the opposite end. Now the problem is Poisson distribution carries on forever. It doesn't stop. Unlike binomial that had a very clear, we had 18 trials, Poisson just keeps going, 19, 20, up to infinity. The problem is, once you get to a certain bit, it just starts to get ridiculously small. So you can cap it. We're only interested in 5%. So there's no point in going any further than 19, because at 19, we've got the probability of 0.0374. The probability of getting 19 or more birds flying overhead, so 19 birds or 20 birds or 21, is 0.0374. If I went down to 20 birds, that's only going to get smaller. Now what I'm interested in, 5%. So I just double check that 18 is not above 5. And lo and behold, if I looked at 18 or more, so if I looked in the air and I saw 18 birds, 19 birds, 20 birds, 21, 22, and so on, the chance of that happening is about 0.0633. So it's about 6% chance. That's past my critical value. That's past my 5% level. So the probability of seeing 90 or more birds flying overhead is 3.7. I would reject the null hypothesis there, but if it was in fact correct, I would have made a type 1 error, and the chance of that happening is about 3.7%. The smaller the significance, the less chance you would make a type 1 error. Okay, notice if it was 18, it's above the 5%, so therefore I would have accepted my null hypothesis of 12 in that case. Okay, so that's a recap of what you did last year. I would like you just to think about what a type 2 error in the context of this example would be. So you might want to just go back in your notes, have a think about that question. What's a type 2 error and what does it mean in the context of this example? So a type 1 error was rejecting the null hypothesis when in fact it was true. So a type 2 error is like the opposite way round. If you accepted your null hypothesis, that on average 12 birds fly overhead, but in reality it's actually incorrect. Now that's a lot harder to work out. It's quite difficult to calculate the probability of a type 2 error. And that's why we didn't look at it last year. We looked at the probability of type 1 errors, but not the probability of making a type 2 error. So in this case, it's the other way around. It's accepting the null when in fact it's true. Whereas a type 1 error is rejecting the null when in fact it was correct. Right, grab your notebooks then please. So in your notebooks, we are looking at errors in hypothesis tests. Now you've got this down from previous, but there's absolutely nothing wrong with making sure that you've got it down again. All right, so we've got in real life, either the null hypothesis is correct or the null hypothesis is actually incorrect. And in some cases, we'd never know that for a fact because we can't check every single situation. But in real life, there is actually a true value. It's either definitely true that null hypothesis is correct or definitely false. What we can do is we can run some tests, and the test results can say either the null hypothesis is rejected or the null hypothesis is accepted. Okay, so those are our test results. Now, hopefully, the situation will be that the null hypothesis is rejected, and because in real life it is incorrect. Or the other ideal situation is we accept a null hypothesis, and the null hypothesis is actually correct. Those two are spot on. Those are what happens. But sometimes what happens though is the other way around. So if we reject a null hypothesis, but in fact it is correct, so our test results say reject it, we don't believe your null hypothesis is correct, but they do run a test again, they are actually correct, then that's a type 1 error. You've made a type 1 error. And the other way around is true as well. If we accepted a null hypothesis, someone else comes along, runs a better test, and realise actually we're wrong, what we've done there is we've made a type 2 error. Because we accepted a null hypothesis when it was in fact wrong. Okay, so that table is just a way of trying to remember between what type 1 and a type 2 error is. There's no easy way of doing it. So if you haven't got a very good memory, try to remember it just before you go into that stats exam. Okay, you accept the null when it's true, it's a type 2. You reject the null when it was correct, it's a type 1. So what we're going to look at is what's the probability of a type 1 error. So we've actually done that already. So the type 1 error is equal to the actual significance level. So not the significance level that's given to you in the question, but the actual significance level when you calculated it. So for example, in the binomial and Poisson, although in the previous examples we wanted 10% and we wanted 1%, sorry 5% wasn't it, it was 10% and 5%, you'll notice that our final actual probabilities of the type 1 error were not those. Those weren't the actual significance levels. So for binomial and Poisson, or any discrete random variables, then you calculate it depending on where you cut off and accept or reject the null hypothesis. Now, if it's not a discrete distribution, if it's a continuous distribution, like a normal distribution, or later on you'll be looking at an exponential distribution, those ones are easier to calculate because they are the actual significance level that you're given. So if someone says, I want a 10% significance level on a normal distribution, then the probability to make a type 1 error is 10%. It is exactly what they say. What's the probability of making a type 1 error on a 1% significance level? It is exactly 1%. Okay, that's true for any continuous distributions. So discrete are harder because you've got to calculate what the actual value is, like we just did on that binomial Poisson, whereas continuous is a bit easier. And you do more continuous distributions later in this course. So let's have a look at this example using normal distribution. So I want you to just get it down in your notebooks then, please. Cut it down a little bit, but not too much. So a company weighs a sample of 18. There's a key word there with the word sample coming in. 18 of their products and believes they weigh more than the label states. The products are normally distributed, so it's telling us there what the distribution is. A mean of 140 and a standard deviation of 4.5. The company will reject the null hypothesis, so they'll reject that their mean is 140 if the weight is found to be greater than 142. So that's our critical value just there of 142. I need to find out what the probability of getting that is. Find the probability the company makes a type 1 error in this test. So if I can find that critical value, that would give me my significance level, and that significance level will be the probability of making a type 1 error. So what have I got then? Well, the distribution is defined as the distribution of the sample means. That's why you've got the X bar on top. Okay, whenever they're talking about a sample, you're not going to talk about X, you're going to talk about the sample means. The sample means is normally distributed, it will be, with 140 as the mean, which we can see just there. But the standard deviation is not 4.5. You need to go very careful that you don't use the 4.5. The standard deviation of it leads to the variance of 4.5 squared divided by how big your sample is. The bigger the sample, the smaller your variance. So it's important to make sure that whenever you see the word sample coming up in these questions, you're remembering to take that into account when you work out your distribution. So there we go. I've got that. You'll do these plenty of times. So get used to it. Once I've got that, now I can state my null hypothesis and my alternative hypothesis. So I need to check the wording. The mean is 140. I can see that in the question. The company believes they weigh more than the label states. So the label's saying 140, but they believe they weigh more than the label states. So we think that our average, our mean, is greater than 140. That's what we're going to be checking. What's the probability of getting greater than 140? So we need to find the probability of the null hypothesis would be rejected. So what do we get then? what's the probability that using this distribution just here, we get greater than 142. So you can get your calculators using your normal distribution button on it, and we're looking for the probability of that. So put your mean in, put your variance into your calculator or your standard deviation, which will be the square root of that, put it in your calculator, and then use what value is greater than 142. And your calculator will tell you the probability of getting that is about 0.0297. So roughly about 3% chance of getting a greater than 142. So that will be your significance level. That is your cutoff point. Your significance level is 2.97 because that's what the company have said. So that value just there is the significance, but it's also the probability of making a type 1 error. Because when you're talking about normal distribution or continuous distributions, the significance level is always identical to the type 1 error. So when you carry out a hypothesis test, you have an acceptance region and a rejectance region based on H0. So what we're going to look at now is we're going to look at what's the probability of making a type 2 error. So it's a little bit more tricky. So let's have a look what that means then. So when you've got H0, if your test lies in this region, you would accept your null hypothesis. So we have what we call an acceptance region. So you run your test, and if your value falls within here, we say, yep, that's fine, we can accept our null hypothesis. We haven't got significant evidence to reject H0. If we pass this critical value though, what's going to happen is we're going to get into the rejection region. So the value we might test might be something that's gone past that critical value. It's here, and we say, right, we have significant evidence to reject the H0. Okay, that's what we've been doing all along at the moment, checking against a critical value. If you accepted the null hypothesis, but it's actually incorrect, you've made a type 2 error. So we've talked about that already. I've accepted it, but in fact it was incorrect. So I've sort of done that. That's more likely to happen near this value. So I might have gone there. I might have said, oh, okay, it's not past the critical value, so therefore I'm going to accept H0, but in fact it was actually incorrect. So what we need to do is calculate that. Calculate the probability of making a type 2 error. We need an alternative H0. We can't just do it from that single value. We need another H0 to compare it with. Another alternative hypothesis. Okay, so when we talk about the alternative H0, this can also be what we call the actual true value. Maybe someone comes along and says, look, I've actually worked out the actual true value. And from that actual true value, you can calculate the probability you made a type 2 error. So it depends on which distribution we're looking at. It's the mean for a normal distribution, it's probability for binomial, and it's the rate for Poisson. Okay, they could actually be the true values. So the alternative H0 that someone comes along and says, we've changed our test, we've changed what we've done, we've taken a bigger sample, and we found our H0, a new H0. Now that can be used to produce a new distribution. Okay, so we're going to change it to a new distribution around that new H0. And what we want to do is test whereabouts our old value was in comparison to that new one. So it depends on which one you're doing. So we've got our new H0, so we rewrite our distribution depends on that new H0. And then what we do is what I just said a minute ago. We test our previous value and we test whether it is less than the critical value of this new distribution. What's the probability of that happening? Okay, and the probability of it happening will give you the chance of making a type 2 error. Now, when you look at it, if the H0 is very close to the original H0, you've got a higher probability. It's quite difficult to spot a difference there. So you've got a very high probability of making a type 2 error if someone comes and gives you a new H0 which is very close to the previous one. Whereas if it's further away, in fact it could be well within the rejection region, then you've got a lower probability of doing it. So a real world example of this could be this. A 12-year-old's party, the average age of the guests is obviously going to be 12 years old. Okay, it makes sense. The average age, not including all the parents or anybody else there, the average age of just the party goers is 12 years old. If you claim the average age is 13 years old and then test this hypothesis, it's quite likely that you would accept 13 years old because 13 years old is really close to 12 years old. Okay, but you'd be wrong. It's a 12-year-old party, the average age is 12 years, so your 13 is wrong. You've accepted it, you've accepted that 13 was correct, but in fact it was incorrect. You made a type 2 error. And because 13 was very close to the original 12, it's very easy to make a type 2 error. Very easy to make a type 2 error. Whereas if the opposite is true, if the claim on average age is 90 years old, then the test it, right, and you accepted that was true, it's quite likely that you made a type 2 error. Very, very unlikely that it would be 90. So the closer it is to the actual age means the higher the chance you make a type 2 error. That's what it meant a minute ago. For two-tailed tests, the acceptance region is between the two critical values. So for example, there's our original H0, there's our two critical values, and we could fall above or below it. We've seen those before. You run a test, you can tell once you run a test which side it's going to be on, okay, whether you're looking at it being greater than or less than. But what you always do is you always halve that significance level before. So the probability of making a type 2 error, you find these two critical values. Right. So grab your notebooks then. Let's have a look. How do we find the probability of finding a type 2 error? So let's put it down as an algorithm then. So we find the acceptance region using our original H0. We find where those critical value is so that we can work out the acceptance region of the original H0. That's the first thing you need to do. Once we've got our acceptance region, we can state a new distribution for an alternative H0. Someone will come along, give you a new H0, and what we can do is we could test our original H0 alongside that one. That might be the actual value. Okay, someone can say the actual value was this. Test what was the chance of you made a type 1 error. Find the probability of getting the acceptance region from step 1 using the new distribution found in step 2. So what's the probability that that acceptance region, whatever I said it was in the first one, is actually going to happen with this new H0? So let's have a go at this. So a test at the rate of which customers enter the shop during a 5-minute interval uses a hypothesis where the mean is 10 and the alternative hypothesis is less than 10. There is a 10% significance level. Find the probability of making a type 2 error when the actual value of that lambda is actually 12. Okay, so while you're getting that down in your books, just get it in context. People come into the shop, 5-minute intervals. We expect it to be a mean of 10, but you actually think it's going to be less. So what's the probability of making a type 2 what's the chance of that happening? What's the significance level? And then find the probability of making a type 2 error when the actual value of that lambda is 12. Okay, so let's have a quick look then. So the first thing we need to do is find the acceptance region. So the acceptance region, if the rate of people coming in was 10 at 10% level. So I can use my calculator. I can work out the values that I want to get less than 10. So I've got my table. I can look at the different probabilities. Probability of less than 13 is about 0.8645. So I definitely accept the null hypothesis there because it's not past the 10%. But probability of getting below 14 is 0.9165. So I've just used my calculator. I've just checked some values. I didn't just randomly get to these straight away. I might have just checked some different values using my calculator, and I've figured out that this is where the critical value is between. Okay, so I know my acceptance region cuts off here. Once I get to 14, I would reject the null hypothesis. So 13 and below is where my acceptance region is. So my acceptance region is if the number of customers coming in was 13 or below, I would accept this null hypothesis of 10. Okay, right. Now I want to calculate what's the probability of getting less than 13 if the actual value that someone comes along is 12. So I'm checking my acceptance region against the new distribution. So my new distribution, which I'll state, is a probability of 12. That's my new one. Last time it was 10. And what's the probability of getting this now? So the probability of getting less than 13, given the probability is 12, is about 0.6815. Now that value I've got there is the probability of making a type 2 error is about 68.2%. So you need a second distribution to make or work out the probability of making a type 2 error. Okay, that's important. That's what makes it more tricky than working out a type 1 error. Okay, now the power of a test. So the power of a test is like the opposite way round of a type 2 error. So the power of a test is the probability of correctly rejecting the null hypothesis. Okay, so a type 2 error was rejecting the null hypothesis when it was in fact true. Whereas a power of a test is the opposite way around of not making a type 2 error. Okay, so just get those two down in your books. So the power of the test is always 1 minus the probability of a type 2 error. So if you've managed to work out the probability of type 2 error, like we just did previously in that shop example, then you can very easily calculate the probability of the test. So to calculate the probability of the test, you must first calculate the probability of making a type 2 error. So if the examiner asks for what's the power of a test, you forget the words power of a test, you think I'm going to work out the probability of type 2 error, and then once I've done it, the power of the test is always the probability of not making that one. Okay, so let's have a quick look at an example of that. So we'll look at a different example. I know there's a lot of writing there, so it gives you plenty of chance to get it down your books. A test on the value of population mean of the contents of a jar filled by a machine uses a hypothesis H0 where the mean is 93.5 and not getting that mean is 93.5. So we're seeing a two-tail test coming in here and a 5% level of significance. The population standard deviation of the contents of the jar is 1.9 grams. Random samples of 8 jars filled by the machine are taken at random elements. There's that word again. Look for samples. Look for the sample size just there because I'm going to be using that. Find the power of the test. So not a type 2 error, but I'm going to need the type 2 error for it. Find the power of the test when the actual means contents of the jar was 94. So I'm going to come back to that 94 grams once I've worked out my acceptance region. Okay, so pause it if you still need time to write it down, and I'm going to have a go at doing it. So first find the acceptance region. So the acceptance region uses the original data. So there's my mean. I expect it to be 93.5. So I've got my mean in there. I've got my standard deviation. Always check the wording. It's a standard deviation. Sometimes I might give you variance. So a standard deviation of 1.9. But because it's a sample, that's going to be squeezed down by the sample size. So it's 1.9 squared to get the variance divided by 8. And I've got a 5% level of significance. So that's going to allow me to work out my acceptance region for this normal distribution. Notice it's X bar because it's a distribution of the sample means rather than just a distribution of each of the items. Okay, so what do I get then? I want to work out what's the probability of getting in between these two values just here equals 95%. So what I've done there is I've used my calculator. I've worked out using my confidence intervals type situation that I've done before to get these two values just here. And that equals 95%. That is my acceptance region. Anything bigger than 94.82 or anything smaller than 92.81 would mean it's outside this confidence interval and therefore it's outside the significance level. That's what I just said there. So check back in your notes. If you're not sure where these two values come from, just check back in your notes and make sure you're happy with how to work out a 95% confidence interval, and that's only because it's not equal to. and the examiners will sometimes tie these things together for that reason. Okay, so our acceptance region is anything between those two values. So what I need to do now is find out what's the probability of that happening with a different H0. And the different H0 we're looking at is a mean of 94. So that's there. Someone comes along and giving you a different H0 value, and you're checking your original against that. Right, so nothing's changed on the standard deviation. That's the same, but the mean has changed to 94. What's the probability of getting between those two? So what do? We do the biggest one all the way up to the biggest, take away up to the smallest. So it's all the way up to the biggest, take away all the way up to the smallest. And I will get a probability of 0.899. That is the probability that I made a type 2 error. Very high probability there. Okay, it's a very good chance you made a type 2 error. So what about the power of the test? So to get the power of the test, you will do 1 minus the probability of making a type 2 error. So it's going to be 1 minus that 0.8991. So the power of the test is 0.101. Okay. What I'd like you to do then is have a look on exercise 5B on page 108 and just have a go at the A-level questions. Most of the other questions you should have had a go at last year, but if you didn't and didn't get an opportunity to do them last year, it might be worth having a go at those as well. Just make sure you've practiced all the Poisson and the binomial examples as well.